So let's look at ideal gas mixtures first. So for ideal gas mixtures, because each component behaves like ideal gas, we can use ideal gas equation of state. So pressure of the component using the ideal gas equation of state. This is, you recognize that because there is mole number in it, so it is in mole basis, not mass basis. So this part, this actually is the pressure comes from PV equals N universal gas constant times T for each component. Now we have changed this subscript for temperature and volume from I, which is for the component, to M, which is for the mixture. And you know why? Because temperature of each component is the same as temperature of the mixture, and volume of each component is the same as volume of the mixture. All right. So if you do this, like pressure of the component at the mixture temperature and mixture volume over pressure of the mixture, these terms will cancel out. You will have number of moles of the component divided by number of moles of the mixture. So that's the definition of mole fraction. So what it means is this. Well, we talked about that. Mole fraction times pressure of the mixture is called partial pressure, or basically for an ideal gas, this is pressure fraction. So the pressure fraction is the same as mole fraction. This is only for ideal gases. We can do similarly, we can use the other law and calculate the volume fraction by dividing the volume of the component at the mixture temperature and pressure by the volume of the mixture. Again, write the first law of thermodynamics, considering that the pressure of each component is equal to the pressure of the mixture, and you can cancel out these terms. Again, you get just mole fraction. So volume fraction of ideal gas mixture is also the same as mole fraction. So what do we do with real gas mixtures? Mixtures that are not ideal gases. There are a number of options. One is if you frequently work or do design on a mixture of gases like hydrocarbons and similar gases that you know a good equation of state for, either Van der Waals, Biddy-Bridgman, or any other equation of state, because the equations of state are not limited to these. So if there is one for the gas mixture of your interest, then probably the most accurate is to use the that equation of state for the mixture of gases and do the calculation, find the properties. What if you do not have access to an equation of state for that specific mixture of gases? Then we use one of these two options. One is use the compressibility factor for the mixture. And I'll show you how to calculate the compressibility factor for the mixture from the compressibility factor of each one or from critical pressure and temperatures. So that's one. The last option is use something that is called K's rule. I'll introduce it in a moment. So let's talk about this for now. And we do a practice problem. So we're talking about real gas mixtures, compressibility factor method. This is the equation that we're going to use. So we have to find compressibility factor for the mixture of gases. And this is the equation that we're going to use. Compressibility factor of the mixture is the sum of mole fraction for that component multiplied by the compressibility factor for that component. Okay. Let's apply that equation, what we learned, into this problem. We have a mixture of 11 kilograms of oxygen, 1 kilogram of hydrogen, and 7 kilograms of carbon monoxide in a container that is 1/10 of a cubic meter. And the mixture is at negative 35 degrees C temperature. So determine the compressibility factor and then find the pressure of the mixture and find the volume of the mixture if its pressure is 5 megapascals. I'm going to stop recording for now, give you guys a few minutes to work on this.